Hello, my name is Paul Hudson and this talk is called Understanding the Standard Library. I run a site called Hacking with Swift, which has over 1,200 articles about Swift, all online, all free of charge. In January this year, I released Swift in 60 seconds, teaching you the fundamentals of Swift coding in videos lasting 1 minute or less. In August, I released a new open source app called Unwrap, where you can learn Swift interactively on your iPhone. It's open source on GitHub. Go and check it out. And in September, I started a new podcast with my friend Sean Allen called Swift Over Coffee. It's at anchor.fm/SwiftOverCoffee. Go and subscribe. My main job, though, is writing books about Swift, including Pro Swift, Hacking with Swift, Swift Design Patterns, Swift Coding Challenges, and more. I now have 16 books, with more coming soon. If you want to get in touch, please do. I am 2straws on Twitter. I am 2straws on GitHub. On Reddit, I'm 2straws, but on Stack Overflow, I am 2straws. Remember the first part, I'm pretty easy to find. Or you can email me at paul@hackingwithswift.com. Okay, today's plan. I'm giving 17 conference talks this year, and every one of them is a new talk, which means I can customize my talk for each particular audience. In this case, this talk's being delivered at Mobiconf. I thought to myself, what kind of coders come here? And the answer is senior coders who want something new, something exciting about Swift. So I thought, fine, let's do that. I'll look around for the best kind of Swift I could find. And where is that? Easy answer. The best Swift is in Swift itself. Inside the Swift standard library is lots and lots of Swift. I love teaching about the standard library when I'm programming with people because it's not magic. It just works like normal Swift code. If you look behind the scenes, you'll see there's stacks and stacks of Swift in the standard library. Fine, over half is C++, but 42% is Swift. And there's a little bit of Python and some other stuff like Objective-C++. Now I could do a talk just on the other part, but let's face it, no one would enjoy that very much. Instead, I'm going to do this talk on the 42% of Swift that's written in Swift. Because this is some of the highest performance, flexible Swift you'll find. It's not just any Swift. It's also highly composable, which means even some complex features take hardly any code. I like to say that Swift is fractally beautiful. The closer you look, the more you realize how clever it is. Look even closer, you appreciate more and more and more. It's fractally beautiful. So we're going to take a really close look at how some of Swift's features are implemented. And we're literally looking at the actual source code to Swift. I'm not really simplifying the code at all. This is the actual source code straight from the standard library. But we're not just doing this for fun. And we're certainly not just doing this so you can go back to your desk in a few days and tell your colleagues how clever you are. Instead, I want you to go back to your desk in a few days and apply these same techniques to your own code. So you'll write faster Swift, safer Swift, and smarter Swift. And the time I have, we'll look at 6 examples in total, and there's going to be lots and lots of code. So let's go ahead and dive in. Here on my desktop, I am on github.com/apple/Swift, where the Swift source code is stored online. And from here, we can go to clone or download, copy this URL to our clipboard, then go to a terminal window. And we want to get a copy of the source code on our local machine. So we're going to start by saying cd desktop, then git clone and paste that URL. And it'll go ahead and download all of the Swift source code to my desktop, including all the history as well, including all the old source code and what's changing and why and so forth. It'll take a minute or so to finish. Boom, it's done. So we now have the complete Swift source code on my Mac desktop, ready to dig through and have a look around. So we're going to change into the directory, stdlib, public, core. Then open dot to open the whole thing in Finder. And here is the Swift standard library. As you can see, mostly written in Swift. Right there, that's all the code. Now a few files like this one here, and this one here, and this one here, end in GYB, which is short for Generate Your Boilerplate. You see, some things in Swift, like floating point types, like arrays for example, have a number of very, very similar variations. For example, floating point types come as floats, or as doubles, or a different type called float 80. But they're the same fundamentally. Apart from the storage size, a double and a float is the same. So rather than having to write the same code twice for both these types, they write it once, they wrap a bit of Python code around it to make it go twice at compile time, and that's the GYB. Anyway, put that to one side. We're going to focus on a file up here, which is, boom, this one here, bool.swift. This defines how booleans work in Swift. The actual boolean type itself. It's all existing in the standard library. So we're going to search in here for func ampersand ampersand. This is our first code sample I want to look at here. Let's isolate that code and make it a bit bigger so we can see what's going on. Now, as you can see, the function signature takes up 3 lines of code. Public static func down to Rethrows bool. The actual line of code itself inside, the actual body of the function, is just 1 line of code to do all the functionality for ampersand ampersand, logical and in Swift. And it's just 1 line of code because of the extraordinary functionality it includes. You can see here we have operator overloading. We have auto closures, we have try catch, we have the ternary operator, and we have the rethrows keyword. There's all sorts here going on, and it enables some fairly advanced functionality. Now you should know this and function is useful in places like this. If we say let A equals false, let B equals true, we can then say if A and B print both are true. And this is a number of clever things, you know. We know that B will never be evaluated because A is false. It doesn't matter what B is, and will perform conditional short circuiting. It won't read B because it knows A is false. There's no point continuing. So A is our LHS bool, something on the left-hand side, LHS, that is a Boolean value. But B, that's our autoclosure throws bool. And it's autoclosure because this B could be some sort of slow function call. And we don't want that to run. You know, if A is false, there's no point in reading that slow function call, so you don't want to do it until we absolutely have to, if A is true. And this autoclosure effectively wraps slow function in a closure. It treats it as a function in itself that will only be run when it's necessary. Then there's this throws keyword. That means this thing might throw. So we can write code like if A and try B. It means this right-hand operand can throw, but doesn't it must throw. Which means we can also write if A and B without a throwing function. It doesn't have to throw, so this code is fine. You can use throws and try with non-throwing function, and that's where the rethrows keyword becomes important. It means if my parameter throws, consider me a throwing function, otherwise consider me a non-throwing function. And it's used over 200 times in Swift. It's really, really useful. Here's the code, the complete code, for the nil coalescing operator. You can see here, there on the left-hand side is an optional T of some sort. The right-hand side is a default value. Again, autoclosure throws returns a T. It then reads the optional. If it has a value, it unwraps it and returns it. If it does not, it tries using the default value. And again, here's our friend rethrows, because that default value might throw, it might not. But if it does throw, then a nil coalescing operator also throws. But if it doesn't throw, it will not throw. So let's head back to our code, and I want to show you how this looks in a real example. So make a new playground, blank, on my desktop, and make it a little bit bigger, and scrap line 3. So I want to show you an example of rethrows in action in some real code we can use. We're going to write some code that has a fetch remote function that fetches a remote string, and that is going to throw because it might fail with a bad network or whatever. We'll have a fetch local function that fetches a local value, and that will always work because the local data is always there. And then we'll have a generic fetch user data function that will either fetch remote or fetch local, depending how we use it. So let's begin. We'll start by defining some errors that can happen with our code. So we'll say enum failure is type of error, case bad network message string. That's one example error. Then we'll have case broken, any other type, and then the enum. So those are our errors we can throw. Now we'll write the fetch remote function. So we can say func fetch remote throws returns a string. Inside there, some complex variable code, then we'll always throw a bad network message saying the firewall had an error, and end the function. So it's always going to throw, just for testing purposes. Now for our fetch local function, this will also return a string but will not throw. So we can say func fetch local does not throw, returns a string. This will always work, of course, return Taylor. End the function. So that's fetch remote, throws, returns string, and fetch local does not throw, returns string. And now we'll have a general purpose fetch user data. It'll take one of those two functions, call it, and print out what it gets. So we can say func fetch user data using some closure, which throws, returns a string, itself throws. Inside there, we'll do let user data equals try closure, then print out what we got back, and end the function. So that would take one of those two functions, fetch remote and fetch local, call it, and print out what it got back. So let's give it a try. We'll try running this using fetch local. So we'll write do try fetch user data using fetch local, catch a bad network message. If that happens, just go ahead and print it out. So print message, then a Pokemon catch all, print fetch error. And this code works great. You can see it's printing out received Taylor. It's exactly as we expected. But we know that fetch local will never throw. As a result, fetch user data will never throw. And so having to write do, try, and catch and so forth for something that will never throw is very annoying. And that's where Rethrows comes in. If we change fetch user data from throws to rethrows, now we're telling Swift more information. If I run that code again, it should, all being well, tell us, boom, no calls to throwing functions occur within try expression. It can now understand that fetch local never throws, so fetch user data never throws. So the do, try, and catch is not required here. We're giving Swift more information about our code. Fetch user data only throws when its closure throws. However, if instead of saying fetch local, we had said fetch remote, that does throw, and so fetch user data will throw, and so here the do, try, and catch is required. We're giving Swift much more information about our code, which means we'll only have to use do, try, and catch when we use a throwing closure with fetch user data. And we don't do that, we don't have to use do, try, and catch. It's much, much nicer. So we're giving Swift all this extra information to make it work harder for us, so we can spend our time doing much more important things, i.e. arguing on Twitter. So I'll go ahead and put that thing into the safer box. Let's go ahead and move on. Back in Xcode again, I'm going to go ahead and scrap that playground and scrap bool.swift. And then back in Finder, let's change files. Let's scroll up. Look for, there we go, assert.swift, one of my all-time favorite files. If we scroll down, you find my all-time favorite function, which is a bit strange to have one of these things, but I do have one. There we go, func assert, love it. Use assertions are absolutely awesome. But here though, a bit further down to here, the precondition function, my second favorite function in Swift. Again, let's isolate that code and center it neatly. If you haven't seen this code before, let's just walk through it quickly. It's saying if we're in debug assert configuration, i.e. if we had pushed our app using Xcode directly to an iPhone, and if our condition fails, we're using precondition with, then trigger an assertion failure saying the precondition failed with our message, a file name, and a line number. A very pretty error. But if we're in release configuration, i.e. we're running from the App Store builds, then still check our condition and still cause a crash if that condition is false. So in debug mode, we get a soft crash, but in release mode, we get a hard crash. Either way, this thing will crash, which might sound stupid, but bear with me, this is actually really, really useful. If you want to see how useful, let's go back to Xcode again. I'm going to switch to a terminal window, And what I'm going to do is I'm going to run the grep command to figure out how many times this is used inside Swift itself. So we're going to run the command grep precondition open parens star. Look for all preconditions in Swift. And we have write back mutable slice, we have unmedged opaque string, we have substring, string variant, string storage, stride, set variant, set builder, range paceable collection, and so forth, lots of times. In fact, if we run that command again and pipe it through wc-l, count the lines, you'll see 256. 256 times. That is how many times Swift will unconditionally crash your code, even in release mode, even on actual users' devices. It's used in many places. Like if you try and call remove last on an empty sequence, boom, crash. Making reverse ranges, i.e. 10 down to 1, dividing an integer by 0, or reading out of array ranges and so forth. These all use precondition. You should not try and do these things. They will crash your code. Again, let's take a look at how this might work in an actual piece of code we write. So I've closed the playground, so let's make a new playground. Yes, blank. Yes, desktop, fine. Yes, replace, it's irrelevant. Make it a bit bigger and scrap line 3. Boom. We're going to write a simple function here that will average an array of integers and return a double. So we'll say in here, func average of scores, int array returns a double. Then we can say inside there that sum equals scores reduce 0 plus and return double sum divided by double scores.count and end the function. Then I have an array of scores like 100, 80, 90. And then let avg equals average of those scores and print out the average. And we'll get back 90. Of course we do, that's the average of those three numbers. That's fine, that makes sense so far. But what if instead of passing in an array of integers, we had instead tried to pass in an empty array? So I'll just do open and close brackets and run the code again. And now we've got to get back is nan, not a number. This is something Swift can't catch. It's an invalid number. It's not an optional nil, it's just a bad number. And if you have one of these nans in your code, it'll screw up your layout or make for weird animations or who knows what. It's an invalid number. You do not want to have this in your program. You'd rather say, don't do this, get out as fast as you can. So it's a good place to use precondition. Don't try and do average of scores for an empty array. So we can modify this by saying, at the beginning of this thing, we'll do precondition. Scores.count is greater than 0. You must provide at least one score. And now if you run the code again, it should refuse to run. Boom. Precondition failed. You must provide at least one score. So it's much, much clearer when we try and use this code. It's way nicer. So let's go ahead and close that and go back to precondition. There's something else I want to look at here. Here's the code again, make it nice and big so we can see what's going on. I want to talk about static string. This is super useful to have in your code. This is a string type that's designed to represent text known only at compile time, which for example is things like let's stir1 equals hello Dave, but not things like let's stir2 equals hello string interpolation name. This is really useful anywhere you have stringly typed APIs. For example, URL string, UI image named, UI color named, NS regular expression pattern, and so forth. You can wrap these things in these static strings, so they're safer. For example, here's an extension on UI image defining a new convenience initializer for bundle named. You use the same UI image named initializer internally, but it has a force unwrap for the initializer result. Because we know this thing must exist because we have a static string for our initializer, which means you must have hand typed the image name. Either it's there or it's not there. It might not, might be not there, maybe, who knows what. That can't happen. You've hand typed it. And the same is not possible with string interpolation because, of course, it could be an unknown string. Interpolation might be bad or user input or who knows what. That cannot happen here. You cannot use string interpolation with this initializer. Let's go back to some code again. Did I close that? Oh, I had to close the playground again, sorry. Make the playground, file, blank, next. Desktop, yes, create, replace. Make it nice and big. And scrap line 3. Boom. Now you should know you can make regular expressions like this. Let regex1 equals try ns regular expression pattern az at. And that'll match things like bat, cat, hat, sat, mat, and so forth. But this particular initializer is a throwing initializer because you might have used a bad regular expression, an invalid regular expression. Of course, we can see this is a hand-typed string. This is either correct or it's not correct. There's no string interpolation here. So we might be tempted to say, let's use instead a try exclamation mark, rather than have to have do catch everywhere for something we know is correct. And that's a fine solution. I would actually encourage this kind of behavior. But a neater solution is to take a new extension on regular expressions by saying extension ns regular expression, convenient initializer, called pattern static string, a string that is typed by hand. And now inside that we can say do try the regular initializer with a pattern, catch any errors that happen, and call precondition failure you made an illegal regex. Then end the catch, end the initializer, end the extension. So there's no more force unwraps here, but it still will not allow illegal regular expressions. So it's a nice little wrapper. And now we can make regexes by saying let regex2 equals ns regular expression with that regex. So it's a really, really clear way of getting rid of the force try for times you know it's absolutely safe. Now again, I do think this is an example where you could feasibly use force unwraps. It makes sense. There are many times when force unwrapping is the right thing to do. But with static string, we can make a guaranteed safe alternative. So that's precondition, so you can clarify exactly what state your code must be in. And static string, so you can ban string interpolation where it matters. I'm going to put both of these things into the safer box, but at the same time acknowledging they make our life easier by forcing Swift to do more work on our behalf. And that is the halfway point. Let's move on. Here's an array of strings. Let fruit equals apple, kiwi, peach. You should know the map method lets us uppercase them all by saying let upper equals fruit.map $0 and we'll get back an array saying apple, kiwi, peach, all uppercased. Now, you and I are mere mortals. How would we write the map method? How would we code the map method? Let's have a look. Back in Xcode, I'm going to reuse the playground this time. Let's scrap these old code here, don't need that anymore. Boom. You'd say something like, well, listen, this has to be an extension on sequences. That much is straightforward. And the function is going to be called myMap because it's our version of map, but it needs to be generic over a T because it's going to return some sort of unknown type of data. So we'll say public func myMap generic over T. This will take some sort of transformation closure. So we'll say it takes a transformation parameter, takes an element of the sequence, throws, returns a transform T. Then the whole thing throws and returns an array of T. Inside there, you might start by saying, let's make a result array of type T, and then loop over each item in the array, enter in self, result append, try transforming that item, then end the loop. At the end, return the result array, and end my map and then the extension. So that's how we might implement map if we were writing code ourselves. Of course, you've now been paying attention to this talk. You should know that my map really shouldn't be marked as throws. It should be marked using rethrows instead, because it should only throw if its parameter throws. So that's how we might implement map. Let's take a look at how the Swift standard library implements map. Back in my terminal window again, I'm going to open a file here called sequence.swift. That contains a map method. And inside there, I'll press Command F and search for func map. And boom, there we go. This is the map method implemented in Swift. This is how they do it in the standard library. Again, let's isolate that code, make it bigger on the screen. Now I could do a whole talk on this one method alone. There's lots and lots packed in here, including, if you notice very carefully, a force unwrap. But here I want to focus on just two things, starting with this first one, contiguous array. Now Swift actually has three types of arrays, and they're all useful in their own way. The first is array. This is the default thing you get when you say, int in square brackets. And it's really useful because it's optimized for efficient conversion between Swift array type and NS array, between Cocoa and non-Cocoa types, which is really good. Then there's array slices. You get this if you slice a main array like 0 through 5. This is designed mainly for short-term usage because it has very serious memory implications. If you have a very, very large Swift array, then slice part of it, that slice will keep the main array in memory even if you try and get rid of the main array, because slice refers to the original array. So you'll be really careful with RAM usage. The third one is contiguous array. This is the fastest of the three, and the Swift team describe it as having C performance. So, if you don't need an NS array bridge, i.e. you aren't going between NS array and Swift arrays regularly, and you don't try and call Objective-C APIs with this thing, you'll find contiguous array is usually faster, particularly for classes. However, I consider using these things an implementation detail. That means you don't expose them in your API, but instead you want to do what Apple does. You want to create, compute, and convert. That means create your contiguous array, do your work inside your method, then convert to a Swift array when you're done. So all folks on the outside see is a Swift array. But there's a second optimization here. This line here, reserve capacity. Before any work takes place, map tells Swift how much space it needs. This is really helpful. Calling this thing means you can avoid constantly resizing your array when you call append. If you have an array of one item and you expand it and expand it and expand it, it will basically double in size as it goes. And Swift will keep on copying each time it has to expand. It's slow. If you call reserve capacity, you can pre-allocate as much space as you need ahead of time. And the cost of that is order n based on the array size. So if you start off with no items and call it then, you'll get maximum efficiency. But be careful. Is your array growth strategy better than Swift's? Swift uses a technique called geometric growth, which means as arrays grow, they double in size over time. So an array might start by holding 2 items, then expand to holding 4 items, then 8 items, then 16 items, 32, 64, 128, 256, 512, 1024, 2048, whatever. It expands, doubling every single time. So you've got to ask yourself, is your growth strategy better than that? Let's take a look at a counterexample, how you can screw things up slightly. Playground's gone again, so make a new playground, blank. Desktop, yes, create, replace. Make it nice and big, and scrap line 3. Let's look at a counterexample, how you can screw up your array growth strategy. Let's say you're a superstitious person, you like playing the lottery. You might have an array called all lucky numbers holding integers. These are the lucky numbers you want to play in the lottery. Then you have a function saying, func, pick lucky numbers. Give me the lucky numbers to play for this week's lottery. Now you know each lottery draw is made up of 10 numbers, so you can go ahead and pick 10 at a time. And you think to yourself, aha, I'm always picking 10 in here. I'm going to reserve capacity for 10 rather than calling append repeatedly. So you'll get the current size of the array and add 10 to it, and then reserve capacity for that many items. And now you can go ahead and say, for underscore in 1 through 10, all lucky numbers.append, int.random in 0 through 50. End the loop, end the function. So this will pick 10 lucky numbers and append them to our array, using reserve capacity to avoid having to do resizing of the array as we add things. But you think to yourself, I can calculate my lucky numbers for the whole year ahead of time, because lucky numbers are timeless, of course. So you might say, for underscore in 1 through 52, pick lucky numbers, end the loop. Let's take a look at this code. I've already said that reserve capacity is an order n operation. But this loop here is also on, and when these two ons combine, you get on squared, i.e. quadratic. Now you might think to yourself, this is setting off alarm bells in your head. Is this a good idea? And of course the answer is no. Don't do this. In contrast, using Swift's append is much smarter. So here's an array of 2 items with a capacity 2 and a count of 2. And when we append to it, it'll be an on operation. You'll have to resize that capacity 2 to be capacity 4 and add your item to it. But the next append will be O1, linear time, because there's space already, so in it goes. So now we have capacity 4, count 4. To append a 5th item, fine, it's another order n, so it'll expand to have capacity 8. And add the item. But add in the 6th item, that's basically free. 7th item, that's free. 8th item, that's free. And again, it expands again for the 9th item to have a capacity 16. But all these adds eventually coalesce down to an order 1 operation. It means that order 1 becomes significantly more common than order n. So the whole thing amortizes down to an order 1, a linear time operation, extremely fast. So, using reserve capacity can make your code faster or make it slower, so use it wisely. So that's contiguous array and reserve capacity. I'm going to put both these things into the faster box. Let's move on. Here's an array of numbers, 10, 20, 30. We can check that all these things are greater than 9. Are they all double digits by saying, let all double digits equals numbers.all satisfy $0 greater than 9. And again, how would us mere mortals, how would we code the all satisfy method? Well, back in the playground, let's have a look. Let's scrap this code. So again, this is going to be an extension on the sequence type. And we'll have a my all satisfy method inside there. This will have some sort of predicate closure that takes an element, throws, and returns bool. And the whole thing will rethrow and return bool if every item passes. Again, it's rethrows because it only throws if the predicate throws. Inside there would say for item in self, if try predicate the item is false, i.e. if we failed the test for this item, then we can return false immediately. This item failed. End the condition, then end the loop. And if we've been through every item and they all pass the condition, now we can say return true and end the method, end the extension. So return true if all items pass the test as you'd expect. But let's take a look how Swift solves this problem. And the file for this is called sequencealgorithms.swift. Let's search in here for func all satisfy. Boom. There it is. Okay. Again, let's isolate that code. Make it nice and big. We've got this amazing 3-line signature again. But the main body of code, just 1 line of code again. But it's a bit hard to read because we have this not predicate backed up by a not contains, which the double negatives kind of hurts my head slightly. But let's break it down a little bit. What we're saying is this thing, the test returns true if each item passes. That's the point of the predicate thing. Is this thing a double-digit number or not? But we flip that around. Return true if the item fails the test. Then there's this form of contains, which means return true as soon as any item returns true for its closure. But we again flip this thing around. Return false as soon as any item returns true for its closure. So the whole thing means return false as soon as any item fails the test. Remember I was saying Swift was highly composable? This is that in action. You know, that one new method, all satisfy, is actually just a call to contains internally. It's beautiful. We can use this code ourselves. Let's go back to our playground again. Did I keep it around? There we go. Boom. Kill that code. And let's look at how we can use the same contains method, to compose functionality in our own code. So the absolute basics, you should know if you have an array of strings like let albums equals red, fearless, reputation, we can say print albums.contains reputation. Does that string reputation exist anywhere in the albums array? The same contains method, name at least, exists on strings. So you could say let phrase equals my favorite album is reputation and print phrase.contains reputation. Does that string contain reputation anywhere? But now we can use that wonderful composing contains method to run a function within the function. We can say let contains any equals albums.contains where phrase.contains and print that out. And now what we're saying is do any of red, fearless, reputation appear in the phrase my favorite album is reputation? So it'll run through it. It'll say, my favorite album is reputation dot contains red, false. My favorite album reputation contains fearless, false. And finally, my favorite album is reputation contains reputation, true. But why stop there? Combining functions is powerful. Swift lets us build new functions by combining existing ones. And to demonstrate this, we're going to do a little bit of code archaeology. So back in my desktop again, I'm going to switch to a command line and run the command git tag. Show me all the tags for Swift over time. And you can see lots of daily snapshots here. Let's scroll up the way through 2017, 2016, Swift 4.2, 4.1, 4.0. Let's go way back to the ancient years of Swift. Let's do Swift 3.02 release. I'll copy that to my clipboard and then scroll way down and run git checkout and paste that name. So I'm asking Git, the source control system, to roll Swift back to an earlier version in time. And I'm doing this because at this point, the Swift team, it's obviously the Wild West days of Swift 3.0, they were far more experimental in what they were trying out. And there's actually a separate file called Swift Experimental, which contains some interesting things. So I'm going to go up a directory and go up one more. Then open that in Finder, the main standard libraries folder. Boom. And now there is this internal directory right here, which contains Swift Experimental, which itself contains Swift Experimental.swift. Let's open that in Xcode. Make it a little bit bigger so we can see what's going on. Okay. So there's stacks of interesting mathematical operators in here they were toying around with. There's lots down here, using cool math symbols for sets. It'll do things like set subtraction, set unions, set intersections and so forth using these math symbols, which are really cool. But here we want to focus on this one bit of code near the top, which is a mathematical composition operator. It's quite long, so I'll add a line break. Let's do one here, and then one here, boom, and then one for a return value as well. There we go. Okay, so this is the code we're going to look at here. Once again, let's isolate that code and make it nice and big. Now there's lots going on here, so let's break it down into little chunks. This parameter, this is a function being passed in that will accept a t and return a u. It's generic over t, u, and v. This thing will take a t and return a u. So it might take a string, return an integer, for example. And the other thing, g, that will take a u and return a v. So it might take a float and return a double, for example, who knows what. And the whole thing returns a new function that takes a t, returns a v. So what it's really doing is merging these two functions together into a single function, like a big long pipe being joined together. The first one took a t, returned a u. Second one takes a u, returns a v. So the whole thing takes a t, returns a v. It's like strapping these two bits together. Now, I want to show you this function in action being used in real code. But first, I'm going to make two changes. Firstly, this mathematical composition operator, like a degree symbol, is very hard to type. So often you'll see it replaced by something else. A common one is triple angle brackets or triple Pulp Fiction brackets if you're cool. And the second change I'm going to make will make maths people totally cringe, but trust me, it flows much more easily in your code. I'm going to switch F and G, and you'll see how natural this looks in action in a second. So let's go ahead and use that in code. Let's scrap all that and head back to our playground, there we go. Scrap all that code. Okay, so we're going to start by declaring a new operator precedence for doing composition. So we'll start by saying precedence group composition precedence associates to the left, which means if we have more than one of these triple angle brackets, they move to the left rather than to the right. They bind to the left. Then we can say our operator, the triple angle brackets, is an infix operator, i.e. it appears in the middle of its two operands, at that composition level. So you can say infix operator, triple angle brackets, is composition precedence. And now for our cool function. Public func triple angle brackets, generic over T, U, and V, has an F parameter that takes a T, returns a U, and a G parameter that takes a U, returns a V, and the whole thing returns a new function that takes a T, returns a V. And then our binding code will do return G, F, $0. That's our new function being made, and end the function. And now we can go ahead and use that. So to start with, we'll define a basic Swift function that generates random numbers. So we'll write func generate random number up to a maximum integer, returns an integer. Inside there, let number equals int.random in 0 through max, print it out so we can see what's happening, then return it. So this takes an integer and returns an integer. The next step is a second function that will calculate all the factors of this number, which numbers it divides into equally. So we can say func calculate factors number int returns int array. Of course, calculating factors in Swift is easy as doing filter. We could say return 1 through number dot filter number percent $0 is 0, end the function. So our first function takes an int, returns an int. Second function takes an int, returns an int array. Our third function is going to reduce this int array down to a string, printing out the factors. So we'll say func reduce a string, numbers int array, returns a string. Inside there, we'll do return numbers.reduce, factors are, then $0 plus string $1 plus empty string, end reduce, end function. So that takes an int array, returns a string. So we've got a chain of functions where one input matches another output again and again. So we can now combine these together using our function composition operator. We can say let combined equals generate random number, then calculate factors, then reduce the string. This makes a new function called combined that it takes an int and returns a string. It's combined all three of those functions together into one big function. So we can now do print combined 100, call it with 100. And the output is, it's picked 60, and the factors are 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, 60. So that is the contains where method, how you can build new functions by reusing existing ones. That's going to go into the smarter box. But you've also seen how we can create new functions by composing existing ones. And with that, I'm running out of time, so let's wrap up. First, go to github.com/apple/Swift and get the source code for yourself. It's all free online. Go and take a look. It's absolutely brilliant. And just start digging through it. Open up files that interest you and see how they work. We've looked at just 6 things here. Contains where, contiguous array, precondition, reserve capacity, rethrows, and static string. But it's an absolute gold mine of functionality and brilliant implementations. Go and have a look and see what you learn. I guarantee you'll think it's pretty awesome. Thank you very much.